right. Then it's my great pleasure to introduce our next talk, Finding Vulnerabilities in Internet-Connected Devices. I think after this talk, you'll never look at polyphones and conference microphones the same way, probably. Pascal Zenker and Christoph Wolf are going to talk to us about how they've been hacking these devices, finding vulnerabilities in them. Our two speakers are both Berlin-based internet security and web analysts. And I think they've been looking at web security for a while, so I'm very curious to see what they did with these phones and why I'm never going to have an internet-connected microphone anywhere near my workplace, I think. Please welcome Pascal and Christoph.
All right. Thank you. Hello, everybody, and thanks for joining our talk today. My name is Pascal. I'm working for Mod0 as security analyst, and with me is Christoph. We're both focusing on web security, red teaming, and mobile IoT web penetration testing, basically. This talk will be about how you can find vulnerabilities in all kinds of internet-connected devices. And if we talk about internet-connected devices, we mainly mean IoT, embedded systems, webcams, conference systems, phones, really anything which is smart nowadays. So we wanted to have this talk because we wanted to show that you can have good results in device hacking without the need of specific hardware expertise or soldering skills. These are obviously super helpful, but we will just try to avoid them because they require good hardware knowledge and specific tooling, which to most beginners is not available. And instead, we will focus on the software. And we also want to show not all bugs are hard to find or require deep technical skills. So basically, anyone can start with it, and we will cover different techniques in basically all kinds of skill areas. And lastly, hacking IoT and embedded devices is just a ton of fun, and we really want to motivate people into getting into it. So this will be the agenda for today. We will talk a little bit about our research target, which we will use as an example today, the poly conference speakers and telephone systems. Then we will talk about a research process that we apply to these kind of devices and that hopefully you can use as well. And in the end, we will talk about our results, but also how you can basically show the impact of your results after you did the research. And hopefully in the end, we will have some time for questions. So there is already a tons of good beginner talks out there. And so we really wanted to do things a little bit differently. And that's why we need to talk about the company Poly. Poly, or Polycom, is a very popular vendor for video, phone, and conferencing hardware, and was bought by HP in 2022. It's a super interesting target because they have really interesting feature set. They run on Android, they have support for Teams, Zoom, Skype, a native zip client, and they have a very restricted launcher, meaning you cannot really leave the initial application. It's supposed to be fully locked down. You don't have any support for Play Store apps, and there's a custom settings menu which basically prevents you from using the normal Android settings. And they have a lot of different interfaces. They, for example, have LAN or Wi-Fi, but also Bluetooth, and can be configured through a web management interface, which makes their feature set really interesting for large enterprises because you can configure a bunch of these devices very quickly. And in summer this year, a client asked us to look into these kind of devices, basically the two one you see on the slides. The Trio 8800 is a conference speaker, which you can put in your meeting room. And the CCX is a smart telephone with team support. And we found several vulnerabilities in these devices. And we will talk about them today. We have reported them to the vendor in a coordinated disclosure process, and the process was quite nice. Both Poly and HP answered super quickly, very transparently, and took it seriously right from the beginning. So we want to say thanks to them for that. And also in the end, we will link the disclosure report. If any one of you has these devices in use, you may check it out. So during the disclosure, it turned out that not only the 2 devices we looked at were vulnerable, but actually there's a whole bunch of their systems which is vulnerable to that. And all of them should be fixed, or at least there should be mitigations out by now. And with that, we have the very, I would say, rare opportunity that we can give this introductory talk, but we can also give you real-world examples for the vulnerabilities that we want to look into and that we want to search for. And we think that's great because it really illustrates the methods itself. And if you want, you can buy a device for yourself and do a jailbreak or solve the challenges like in a CTF or something. All right, now Christoph will start to guide you through our research process and show you how you could basically find vulnerabilities like these.
So, first up, we'll introduce 2 important concepts which we'll use throughout our talk. The first one is basically that vulnerability research on a very high level is a rinse and repeat process. In the first step, we enumerate a part of the attack surface of our target. We will then evaluate any potential issues, and at last we will exploit any weaknesses that we find. And then in the next step, we will broaden the attack surface. We do this either when we get stuck or when we have exhausted all of our options. And we can do this by either looking at new features, which we haven't looked at yet, or by using some newly gained access from one of our successful exploits. And then we will rinse and repeat. Today we will show you the vulnerabilities which we can divide in basically these 2 kinds. They are business logic vulnerabilities and technical vulnerabilities. On the business logic side, we can exploit actual design flaws in an application by using the device in a way that developers did not really think about. They usually do not require much technical knowledge, but rather thinking outside the box in the context of the device or application that you're hacking. And that makes them especially interesting for beginners because, yeah, you can get pretty easy results without doing a deep technical dive. And an example for this kind of vulnerability would be a web shop where you can maybe apply the same discount code multiple times in a row to really make something super cheap. And on the other hand, we have the technical vulnerabilities. These are usually the programming failures, the one you have probably heard of before, something like a buffer overflow or an SQL injection. And we will see more examples for this later on in our talk. Our research process will use the concepts we just showed you, and this will be our research plan. We will first use, or rather misuse, the device. We will then enumerate exposed services, verify and learn from already known vulnerabilities, and then later on we get to the more advanced topics like fuzzing, web API pen testing, and some reverse engineering. But first up, we will start using our device, and we do this to actually getting to know our target so that we know what it does and what functionality it offers. We really want just at this phase, explore the device, just visit every menu, use all the functionality we can find, just being really curious users of the device and trying to find out what can it offer to us. It's also usually very helpful if you read the available documentation or a manual and just in general find out anything that you can about the device. In our case, with the pen test assignment we had, the customer was using the phones in a somewhat unprotected area, and so to them the physical attack vector was very important. So naturally, this was one of the first attack surfaces we looked at. So we, as Pascal said, there's a rather locked down interface which you get by default, and we wanted to escape this, what you call normally a kiosk mode. For example, if the phone is in Microsoft Teams mode, then you cannot actually ever leave the app. So all the device settings are inside the Teams app, and there's not like something like a home button to get to a home screen. You just are stuck in the Teams app. And when you're not in Teams mode, you have like a somewhat of a launcher, but you can only launch the applications for which the device has been configured before. So we now want to leave this restricted UI to maybe access a browser or maybe even install a malicious app. And to do this, there are various tricks we can use. So one of the examples would be kind of obvious, but swiping in from the edges, maybe see if we can get maybe the notification tray, find a button that gets us to the settings or something. On the other hand, we can also try to open other applications. A pretty good trick for this is usually trying to long press on images, see if you can maybe share them to another app, then the other app opens. Also, you can also oftentimes start web searches. For example, if you press long on text and you get a context menu, you can say web search, then the browser opens up, and then you have access to the browser. And if you get to the browser, you can then use this to maybe download files, even executables, and run your own code, or at least browse the file system, or maybe through custom protocols like Mail2, you might be able to open up the mail application. Something else to always check for is booting into different modes, for example, like Windows Save mode, or when you want to get to the bootloader on Android, you usually have to press one of the volume keys while booting. So you can try while booting up, pressing any combination of keys and see if you get different results than booting normally. Also in general, you want to examine the device physically very closely. You really want to find all the ports, all the buttons that they have. And especially with the ports, if there is a USB port, you can usually do all kinds of shenanigans where you connect different devices and see how the device you are hacking reacts. You might want to attach something like a thumb drive to get the file access, or a printer to get a special dialog. And also you can usually connect the keyboard. And that is actually something we did, and we connected a keyboard to our CCX VoIP phone, and then we tried all kinds of key combinations. And Android has some built-in keyboard support, so there are some default key combinations that you can use. For example, Alt-Tab usually switches the frontmost application. And when we tried this in the CCX and Teams mode, it was kind of a strange behavior, which you can see in the screen recording. So here we see the normal Teams app on the phone, and these are the basic settings that you get, so it's basically all included in this Teams app. But now when you try to hit Alt-Tab once, we get this black screen and kind of not really getting there. But if we hit it in quick succession, we suddenly get to this screen, which looks completely different than the Teams app. And this is some native app that was apparently running behind the Teams app and which we can now get to. This allows us at least to see a little bit more than the normal Teams settings. We get some special diagnostics and can actually execute pings and trace routes in the network. And in general, we can also take a look at business logic vulnerabilities here. These, as I said, do not require much technical skills, and here's a great example of this kind of vulnerability. So this is on the Trio. The Trio settings look pretty similar to the ones that we just saw, UI-wise. And so they usually have an admin-only area, so you can browse some diagnostics without knowing the admin PIN, but for actually changing important settings, you need this administrator password. And this, you see the screen here where you have to enter the password. And this makes sense if you think about the Trio as a conference speaker. It will be just sitting in your conference room, you might have guests over, and anyone could just mess with the device, either intentionally or by accident. And so what we did, being curious users of our device, we will just look around the menu where we don't need a PIN and then just see what we will find. And we did indeed find something. So in this status/cloud status page, we found this neat entry called registration code. And there it said, okay, your Trio is unregistered, and said, this is your code, you can go register it at lens.poly.com. And so we did. We went to our browser, went to lens.poly.com, created a free account and registered our device. And we just needed this PIN we just got and a name that we could choose. After we did this, we got this pretty looking interface where we saw our device's details, local and public IP address, the firmware version. But there's also the settings area down below here. And this actually allows you to completely manage the device. This includes the harmless settings like the ringtone. But you can also just set a new administrator password, and you can also launch a packet capture if you want to see all the packets that are sent and received by the device, all remotely from your browser. And there's even another handy function in here. In this more actions area, we have this menu point called initiate call, which gives you this neat dialog where you can just enter any phone number and the device will call you. So you can listen in on any conference room where you have done this before and then just have the device call you, and you are on speakerphone, you can just listen in, you can talk to the people however you want. And this is a business logic vulnerability because at no point in time we had to enter our administrator's PIN. We didn't know it. We just had access to the device, we saw this code, we used it, and now we have the full admin capabilities. The only preconditions for this is that, of course, you need physical access for the device, which might be tough. The device must not yet have been registered before, and it needs to have network access to Poly service, because otherwise you cannot enroll it. So next up, we will enumerate any exposed services. And this is pretty similar to the exploratory phase, which we did physically. But in this case, we will actually use some tooling to check what ports are open, what services are running on the device, and just find out what is going on there. And to use this, we use tooling. Nmap is very, very common, but there are other options exist, like Nuclei, for example, which can do also some service enumeration, but it's also a vulnerability scanner, so you might find some already known vulnerabilities in some components of the device. If you're a beginner, it probably makes the most sense to just focus on the protocols or services that you know already. For example, if there's a web server running there and you have some experience with that, then you can check it out. If you see file shares, then you might want to check out these. Anything that you know already will probably be a good first start. Of course, the more complex protocols might offer also more attack surface, as they are usually also for the developers harder to implement. There are no pre-existing libraries to use. And so this might require a little bit of a deep dive, but it can also lead to good results and a fun challenge as well. So on our device, as you can see on the top here, we found a port 443 open, and there was a web-based management interface, which is, I think, very common for these kinds of devices. And in our case, it is first protected by a password prompt, where you need the same password which you need for the settings. If you should ever be faced with that login screen, the default user password is 123 and the default administrator password is 456. Yeah. And here again, we enter another iteration of our enumeration and then broadening the attack surface. So we again, just like we did in the menus before, go curiously exploring all the functionality, trying to understand the business logic, putting on our hacker glasses, seeing what functionality might be interesting to us as an attacker, and how can we get there in the UI. And also think about what protections are in place and where. And so we go looking around and we come to this software upgrade screen, and then we look at this drop-down menu and we see this is not really about software upgrades. You can actually do software downgrades here. And in general, this is not a good idea because usually these updates also do fix some security issues, right? So yeah, this is called rollback protection if you protect this, and this is obviously missing here. And as you will see in a couple slides, these older firmware versions with known vulnerabilities will come in handy. Another thing that we found was that when we wanted to change the administrator password, you needed to enter your old password, which is a pretty sensible security boundary here again. There is another neat management feature, which is configuring device by uploading the XML format, which just sets all the settings that you want. And this XML file you can just upload without knowing a password, but you can also set the local administrator's password. Again, another classic business logic vulnerability. They figured at one place we need this protection, you need the old password to change it, but for the configuration, they just did not think about this. Our next step now is to verify and learn from already known vulnerabilities for our devices. And you should always do this as early on as you research as you can, because it really can give you some good hints where you want to look for any vulnerabilities. And also, similar devices might also have similar vulnerabilities. For example, if we have a broad catalog of devices from a company like Poly, then there's a good chance that the code between these devices is at least somewhat shared, and that the vulnerability that you have in one device might also apply to your device. So always check if any vulnerabilities for similar devices, maybe if you're able to reproduce these on your own. Here we also list some common sources where you can check for known vulnerabilities. In our research, we found a very cool blog post which actually talks about an authenticated remote code execution in the Polycom Trio 8800, which we had to look at. And for us as attackers, remote code execution is really just the holy grail. This is the highest impact our attack can have, because if we can execute our own code, we can do whatever we want with the device. And this blog post also revealed some cool and to us previously unknown attack surface which we hadn't heard about yet, because there is an undocumented diagnostics telnet which you can also enable via the XML configuration. And this they then use to execute code on the device. So now that we've heard about this telnet, we will again broaden our attack surface and dive into our exploration phase there. We enable the telnet server using the configuration file, and in our nmap we can see that port 1023 is now open. So we then connect to the telnet, where the user is always Polycom and the password is the administrator password you had set. And then you get this shell with some predefined commands. And lots of these seem very custom. And they allow you to do stuff like seeing the currently running configuration as XML, but also see the internal CPU load, basically lots of diagnostics functionality. So in the blog post, they found that some commands are basically just passing their arguments to a shell, which will then execute a command, for example, the ping. And so what they did is they did a command injection using the semicolon, which in most shells separates two commands in the same line. So they ping something and do semicolon ID. And then you will see first the ping is trying to be executed, it fails, and then you see the output of the ID. That is showing us that our command is actually run as root user, so the highest possible privileges. And then in the blog post, they then use this to enable ADB, which is an Android debug feature. It basically gives you, apart from other things, a shell on the device, which is just unrestricted. So on our Trio, on a newer firmware, we couldn't reproduce this. So we did the same thing. You can see it down below. We execute the ping, semicolon ID, and it just says the error for the DNS name resolving is now handled, and it fails completely. The ID is never executed. But a kind of common thing is for vendors that they only fix the security issues exactly where they are found without fixing the underlying issue systematically. So we thought, what other commands do we see that might also be just passed to a shell? And then we found the top command, and we found it works the exact same way still. Yeah, as you can see, this is still injectable, it is still running as root, and we have now code execution as root on our Trio. On the CCX, we couldn't actually do this the same way, because there they have a newer major version for their firmware, and apparently there they actually fixed this in a diagnostics telnet, where they pass the command, check for any unwanted characters, like semicolon, and then they just don't execute the command. But in the case of the Trio, we just got full control over the vulnerable device if we know the administrator's password. And now it's my pleasure to hand over back to Pascal, who will tell you about our more advanced topics like fuzzing.
Okay, so now that we already dived into the technical vulnerabilities, we want to talk a little bit about fuzzing. So software nowadays is really complex, and one might even say it's getting too complex to completely manually ensure that it is bug-free. Because the code size constantly increases, but our manual efforts to fix every issue doesn't scale in the same way. And we as attacker have a great advantage, because we only need basically one single mistake that we can exploit later on. And fuzzing is a technique which helps us detecting such cases that were overlooked in the software development process. We basically try to exploit this code complexity by leveraging brute force. And fuzzing is especially effective for languages which perform unsafe memory operations, like C or C++, because there we can look for memory corruptions, overflows, or any issues with pointers. And if you find an issue, this in the best case results in a crash, but in the worst case in an exploitable bug. So this is a high-level overview of the fuzzing process. In the middle, we have the fuzzing engine, or the fuzzer, and the fuzzer gets supplied with user input, the so-called seeds. And with these seeds, we try to have input to a target program, which basically cover as many code paths in the target as possible. The fuzzer will take our seeds, mutate them randomly in different locations, and run them against the target. And then it will observe for interesting behavior. And this is done as fast as possible, so we really try to test a lot of cases in a quick time. The question is, what is an interesting case? So this might be a crash, or a timeout, or in the best case, a memory corruption. And then we can look into these cases later on and see if it's an exploitable bug or a security issue. There is a major improvement over this kind of basic fuzzing approach, which would be coverage-guided fuzzing. And in that case, we or the fuzzer has a way to detect how many code paths were already covered in the target. And that really gives us a better indicator on what kind of mutated seeds are interesting, and we can then put them back in the seeds and start the process from anew. If we get greater coverage, we basically see more of the program and have a higher chance to find a bug. But sadly for this talk, we will stick to a basic fuzzer. It is mostly enough for IoT devices, because there you can usually get quick wins. But if you're interested in coverage-guided fuzzing, we can highly recommend the talk Fuzz Everything Everywhere All at Once, which was here yesterday, and goes into a lot more detail about advanced fuzzing. So how do we go about building such a fuzzer? We knew the web server was written in C++, and therefore we thought it's a very fruitful target for fuzzing attempts. And our go-to for this kind of very simple and basic fuzzing is BooFuzz. We have linked it below. Because BooFuzz is a general network protocol fuzzer, which we can really quickly adapt to all kinds of protocols. There's a lot of examples on GitHub, so you can just look for the protocol you want, find a good example, and then basically fit it to your test case. And there's also a great introductory blog post about it in German by Inside Attack Logic, which we also have linked here if you're interested. So what you can see here is a normal HTTP request to the device, to the management interface. Basically, the device will pass the session cookie, and then it will check if the authentication of us is valid. And from experience, we know that parsers are most often a very interesting target for fuzzing, because there you can just do a lot of mistakes. So how would we go about fuzzing this request? So we basically transform the request into such a test case. We take the legitimate request, and then we define which parts of that we want to fuzz. So everything which is appended here with the static will not be mutated. And the areas which are marked with string will be mutated by BooFuzz string mutation algorithm. And with this test case, we specifically try to fuzz the cookie parsing implementation. We want to have this static parts because we really want the device to parse our package, and so sometimes we need some things to be static to get to the point where we can actually fuzz the right point. The fuzzer then creates random requests, and they might look like this. So, for example, here the fuzzer created a request with a lot of A's and the session cookies value. And if the device would crash now, we might have a buffer overflow or something like that. While the fuzzer is running, we have this kind of output. Here we see different EOF cases, which the fuzzer identifies as interesting, because they might indicate a crash or a timeout on the web server. And now if we look into such a test case, I hope it's big enough, maybe not, but in this specific case, for example, there is no actual value for the cookie. So cookies are always sent in key value pairs, and in this test case, there's no equal sign and no value. And so we thought, okay, let's reproduce a minimal working example and see if there's an actual underlying issue. So the window on the right here shows our connection to the debug telnet, and we use this to basically check if the target is still online. And then we just took a normal request and modified it by removing the session cookies value. So we just stripped the equal sign and the value, and immediately the device crashed and rebooted. So it's a super quick and easy bug to find. We didn't need to wait long. It just took a few minutes. And now, as an attacker, we could exploit this by, for example, just sending this request in a constant loop, and the device will crash and take 3 minutes to reboot every time. So the big question is, what is the root cause for that? And we investigated. It looks a little bit like a memory corruption. And sometimes such a crash is exploitable with binary exploitation techniques. And it's worth looking into that if you have the time during an assessment or in your private time. We wanted to make the most of this research, and we only had 1 week. So we basically reported it as is, because if there's more to be found, this is already enough for the vendor to know there's an issue they need to fix. And if anyone is interested looking more into that and building a full-blown exploit, then let us know. Okay, now we already talked about HTTP, so it's a great transition to actual web and API pen testing. So this is always a big part of our attack plan, because basically all kinds of internet-connected devices use HTTP in some form or another. There's like these local web management interfaces that we already saw, but a lot of devices also connect to some API on the internet, which maybe allows to configure the device or update the firmware or store data. And we need an active machine in the middle position to see and modify the HTTP communication. And there's a lot of tools for that. We usually use Burp Suite. There's a free community edition, but there's also mproxy, which is also great and completely free and open source. But you can also start with your browser's dev tools, if that's something you want to work with. And once we have this setup ready, we basically perform a normal web penetration test. And if we say that, we mean testing for vulnerabilities like SQL, XSS, or command injections, CSRF attacks, IDOS, authentication, authorization bypasses, and so forth. And we could talk a lot about that here, but I think there's already loads of great resources online, and you will probably find something interesting to read about that somewhere else. If not, please come to us and we can give you some hints. So as we said, we always look at the authentication process. And especially on IoT devices, let's say developers get very creative in implementing non-standard auth methods. And for example, here we performed several authentication attempts and extracted the session cookie the device sends us. And we did this with the intention to see if the session cookie is maybe in some kind of another predictable. And normally we would expect every session cookie to be unique, but here obviously something is really wrong because there's a whole block of tokens which look the same. So we were sure we spotted an issue here, but the question is now basically what is going wrong. And that's quite hard to analyze and understand if we only have this limited black box information. So at this point, we again need to broaden the attack surface. And in this case, we will do so using reverse engineering, which is also the last technique we want to talk about today. So reverse engineering basically is the process of understanding how software or hardware systems working by analyzing the individual components. And then we try to reverse them back to a planning phase object that we better can work with. So for example, we have a compiled binary, and then we compile it back to the potential source code to see what's going on. And a good starting place for any kind of device is the firmware. Because if we have an actual insight into the software which is running on, we can always better test. We can dynamically test and verify behavior which looks strange, and often we can even find hidden features or functionality. A lot of times there's also some leftover developer tools which are great for us, and yeah, we always see hard-coded secrets. So how do we get the firmware? Like in the best case, we just download it from the vendor's website. That's most often possible. Interestingly enough, since we did our disclosure, the poly firmware is missing. In other cases, we might use a machine in the middle setup between the device and its backend and intercept the firmware update process and extract the binary from that. And sometimes you can just get creative. So for example, once we had a firmware update tool on Windows, and it downloaded the firmware into a temporary file, transferred it via USB to the device, and then it got immediately deleted. And then we just removed the user's permission to delete files, so the firmware basically stuck after the update process, and then we could unpack it. Yeah, and if the firmware is not signed or the signature is not validated, then at this point you can also obviously tamper with the firmware, right? You could modify it and adapt it to your needs. But we really recommend to do this in the end because you might break your device, and that's not good if it's in the middle of a pen test. If you have an unknown binary format, you can use bin walk. It's basically walking over the file, looking for known file signatures, and it's extract these from the binary file. But we had an Android firmware image here, and there's a lot of existing tooling to unpack the firmware. And once it's unpacked, we can basically walk the file system and see what we can find there. We can use Java decompilers to reverse any Android application files back to its initial Java source code. And with GDRA, for example, we can decompile executables into a somewhat readable representation of the initial source code. And also we can look at the file system and see if there's any startup scripts or services, which are most often very interesting as well. So reverse engineering is very time consuming and it takes some practice. But you shouldn't be discouraged because you get better really, really fast. And also you can always see if someone else did already the work that you are planning to do so. There's a really big jailbreaking and routing community for all kinds of Android devices, and a lot of people already did this kind of things with the device already. And with a little practice, you will get better quite fast. So there's practice challenges called CrackMes, which are basically small reverse engineering challenges that you can work with. And most often, it's not necessary to understand everything. So you can just focus on small sections that seem important to you. So this is the piece of C code GDRA will show you for the session cookie generation. And now we can walk through the code together and see where this issue stems from. So here in the bottom, we have a variable which we call random string pointer, which will basically hold the session cookie in the end. And now we can actually skip most of the part of the code because it's deterministic. We can just implement that ourselves. And we want to see where is the randomness introduced into the token. That's actually here in this rand call. And now what we always do if we have a call where we're not quite sure what this does, we check the man pages. And rand doesn't actually return a fully random number, but a pseudo-random integer. And if the rand can be seeded by the srand function, we basically give a number to the srand function, and then the sequence of the numbers afterwards is always exactly the same if you have the same seed value. So here we see the srand call I talked about, and it's actually seeded with the time. And if we check the main pages for time, we see that it just returns the number of seconds since the epoch. And that's great for us as attackers, because the resolution is way too small, and that's actually something we can fully predict, and we can really know what token is being generated. So just putting this together, basically for every second, there's exactly one session token that will be generated, and it's the same for all poly devices. And this is obviously something which we can exploit. So this is a successful authentication attempt against the device. And the web server will return its time, which will allow us to basically have the number for the srand call. And this is the session cookie, which the web server will return. And now what we did is we just re-implemented the code I just showed you from earlier and can supply it with an arbitrary srand seed. So if we do that, we basically generate the exact same session cookie. And now the question is, what can we do with that? So in short, we can steal a logged-in administrator session. For example, we could just create all authentication tokens for the last 2 hours. It's only 7,200. And then we check programmatically if any of these sessions are valid. And if yes, an administrator had logged in, and we can take over the session. Another approach would be to just constantly try to log in with the session token from about 5 seconds ago. And once an administrator logs in, we can overtake their session. OK, now we've seen a lot of different vulnerabilities. And vulnerabilities are most often measured by their impact, meaning that we as hacker or as pen tester really need to be able to properly showcase what impact we can achieve. And what is often overlooked during this process is that the vulnerabilities don't need to stand on their own. So you don't need to basically show the one vulnerability you found. You can also cleverly combine several issues, and that might be able to increase the overall impact of the individual ones. So here on the left, we have an unauthenticated attacker with network access, and on the right, our goal, which is the remote code execution. And we don't have a single issue which allows us to do this, but by chaining the vulnerabilities we uncovered today, we can actually do that. So starting from the back, we know for the RCE, we want to exploit the command injection we talked about. This one has 2 big requirements. We need a vulnerable firmware version and access to the debug telnet. And let's talk about the last one first. So for this, we need an enabled debugging telnet, which we can do with an active administrator session by just importing the configuration file. And we also need to know the administrator password. And for this, we also have a bug, because if we have access to the administrator session, we can just import a configuration which overrides the password. So the vulnerable firmware version, there's actually poly devices which are vulnerable right from the start, like the Trio 8800. But for the other ones, we just perform the rollback via the web menu. So for all of this, we need an active administrator session, but we already know how we do that. That is the administrator session prediction. So basically, the attack plan is clear. We just constantly try to take over a session. Once we got one, we downgrade the firmware if we need to. Then we import a configuration file, which enables the debugging telnet, resets the administrator password, and then we can exploit the command injection. And we could even speed up this process if we just send our crashing HTTP request every once in a while, so an administrator might be looking into it. So if we do this with all the discovered vulnerabilities, there's a ton of attack path. And we know this diagram is messy, so you don't need to try to basically understand all of it. But we just want to show that the most severe issues that you can find most often don't stem from a single bug, but from multiple bugs. So just don't stop if you find something interesting, because if you have multiple interesting things, it might be way, way bigger impact. So one example would be here, if we have a Trio 8800, we can go a completely different attack chain. If we have physical access, but no credentials, we can just do the lens enrollment we talked about earlier. And once we did the lens enrollment, we can set the administrator password and enable the web server. Then we can connect to an attacker-controlled Wi-Fi, and we don't even need to downgrade the firmware because they're vulnerable from the first place. And then we will basically exploit the command injection and have a remote code execution as well. So this is probably a little bit confusing, and therefore Christoph will walk you through a demo now.
So now it is time for us to demonstrate our attack chain, the one earlier from where we stole the administrator session to getting code execution on the device. And we do this by showing you our exploit script. And to really show the impact of us being able to execute code on the device, we will use an existing tool we found on GitHub that allows us to forward an Android phone's microphone input to our own laptop. Then it's basically a microphone on the laptop, which we then can listen to in real time and record, as we will do right now. And we will use this to listen in on me while I'm having a perfectly normal video conferencing on my computer with a CCX400 sitting on my desk. I really hope the audio will be working. So on the left here, we will have our proof of concept script. On the right, you will see the administrator interface where we will now log in. Our script constantly tries to take over the session with the session from a couple seconds ago, which has just worked here. We have a valid session, and we'll use this now to upload a malicious configuration, enabling the password and enabling the debug telnet mode. Now that we connect to the debug telnet mode using the password we just set, we find that the device is vulnerable to the command injection, and we can execute code as root. If the command injection would have been patched at this point, we could use our downgrade vulnerability to downgrade the firmware to a vulnerable one. And now we use our command injection to basically enable stage 2, which is set up ADB and forward the audio.
Sure thing. Got it. Oh yeah, the new phones are great, by the way. Apart from that, not much from my side, but be aware that we changed the default password for new users to winter@123.
So glad that the audio worked. And this just leaves us. And that just leaves us with a fully jailbroken device. We can now do whatever we want with it. We can pass time at the office by running Doom, but we could also, for example, attack the attached network from the compromised phone, or try to fish for user credentials, by the way, maybe pop up something looking like the Teams app, asking for the Teams credentials. And yes, this pretty much concludes our talk. You will find the advisory page in the top right, and our contact information is also here on the slide. That's it from us.
All right. Thanks so much up until this point. We'll have plenty of time for questions, so if you have a question in the room, please come to one of the 4 microphones, line up, and we'll make sure to get all questions answered. If you're leaving the room already, please do so as quietly as possible. And I'm not sure if our signal angel showed up at this point and maybe has questions from the internet, but I don't see a hand waving right now. All right, microphone number 3, please.
Hello, thanks for the great talk. It was really cool to hear all that. I was wondering, I think I missed it maybe, like, why were the session keys after all so similar?
It was because we did basically a few requests in a second, and for every second there's only 1 session cookie. So if we did like 10 requests in a second, then we have actually the same session cookie.
Got it, thanks.
All right. I don't see any other questions right now. So then I think we'll conclude the talk. Thanks again to Pascal and Christoph.